My name is Dave Watson. I am here to talk to you about experiences with Facebook's C++ library. So this is not all of Facebook's C++ code base. Specifically, we're talking about something called Folly. It's an acronym, a very loose acronym for Facebook's open source library. A very silly acronym. So what is Folly? I've been at Facebook for 6-7 years now, really long enough to see our transition to C++ 11, long enough to see our transition to C++ 14, and I hope a little bit longer. But really, we started with a whole bunch of code in a bunch of different services. A lot of the common code we tossed in a single directory, called common, of course. It was a bunch of excellent code and a bunch of very bad code all mixed together. We wanted to open source some of our cool projects and share them with you guys. You've probably heard of some of them. HHVM, HipHop, Apache Thrift, Proxygen, McRouter, Wangle. There's a whole bunch of open source projects that we wanted to share. And to do that, we had to open source all this common code. So we took a bunch of common code, put it in this open source library called Folly. This code is trying to not reinvent the wheel. We try very hard only to fill in the gaps between what is in the standard, what's in Boost, what's in various other libraries that we use. Originally, we had a very extensive usage of Boost. It's kind of waned over time as more and more has gotten to the standard. So in 2012, we open sourced this library called Folly. We're going to go over some of the pieces in the library today. There's like 50 to 100 different pieces in this library, so I kind of just have to pick and choose. It's a little bit of a spastic talk, jumping from one topic to the next, but it kind of has to be to try and fit in all these different pieces. So a lot of things were in Boost, moved into SCD. As this has happened, we've tried to keep our library up to date. So moving to C++ 11, we of course changed our entire code from Boost shared pointer to SCD shared pointer. We've done other things as well, similar, going from C++ 11 to C++ 14. In C++ 11, in lambda captures, you couldn't actually use unique pointers. So to work around this, we had lots of unique pointers, lots of lambda captures. We made this thing called move wrapper, which is really just a copying wrapper around it that allows you to use the unique pointer in the lambda capture. It was terrible. It's totally a hack. We want to get rid of it. Of course, now we can. C++ 14, slowly updating all our code to remove it. So definitely a living library as we move through the various standards. So let's talk about a bunch of the different pieces. You've probably seen some of these already at other CPP talks. FBString, there was an excellent talk yesterday. Really, it is optimization on the standard string that we'll talk a little bit about. FBVector, small vector, also had another talk. I believe that one was yesterday. Conversion utility and some synchronized locking. FBString, small value optimization. If you have strings under a certain size, it will keep them on the stack. Small vector, the exact same thing, small value optimization. If you have under a certain number of things in your vector, it will keep them on the stack. FBVector is a little bit different. Vectors, when they resize, they have to go and allocate some new memory. They can do this in a bunch of different ways. For example, FBVector actually integrates with your allocator. In our case is jemalloc. It asks it, hey, do I actually just have some extra space here I can just resize into without actually doing anything? So it pulls that trick quite often. Sometimes it's able to coalesce some memory that's actually at the end of the vector itself to just grab some memory, kind of like a realloc. And it's able to pull that trick as well. So these are just faster containers using various tricks. We also have a bunch of other little utility libraries. We have a conversion utility library. It's called to as the name of the function. It takes a template parameter of the type you want to convert from, and it uses the template parameter of the type you want to convert to. It's very, very similar to Boost's lexical cast, if you're familiar with that. It's just a standardized way to convert from one type to another type. So we could have just used Boost lexical casts, and that was actually what we started with. We were using that for a very long time, until someone noticed in perf, like, hey, this is actually taking quite a long time, especially with float types. So we went and updated a bunch of the different conversion utility libraries, wrote some of them ourselves, grabbed some other cool libraries from like V8 for fast float conversion, and we ended up with a whole new conversion utility library. This turns out to be really, really useful if you're not doing this in your own code. If you're still using like A2I or something like that, this is much more uniform and much easier to read. If you end up changing your types, you don't actually have to go through and change all your conversion libraries as well. So I highly recommend using something like this. You guys have probably heard of Synchronized too, so I'm just jumping through some of these really fast that you've probably heard of. Synchronized, very similar to the Java version. We have lots of awesome synchronization tools now in C++11. We have std mutex, we have condition variables, we have lock guards, we have unique locks. We don't actually have something like synchronized just yet. What is synchronized? It actually ties together your lock and the data you're trying to protect. So when you call pushback here in this case, it's actually grabbing the lock when you do reference the synchronized object, pushing back, and then releasing the lock. So this right away solves two of the main problems you have with locking. You can't forget to lock the data. You have to break the abstraction to actually forget to lock the data. So that's solved right away. The other one that is solved, especially with the RAII, resource acquisition is initialization, kind of lock guard and unique lock, is that you can hold it too long. And that happens quite often. You'll often see that show up in perf. You figure out, hey, what's going on? I have a bunch of lock contention here. Oh, I need to like add an extra little block here to make it a shorter lock time. And that just happens as you go through and modify your code. You know, if someone's like, oh, I need to do a little extra work here in this function, not realizing that you actually have this lock guard at the top of the function. So of course, it introduces another problem. It can actually be too short of a lock time now, so you actually have to open a new block if you want to go and do multiple things while holding the lock. In practice, it turns out to not really be that big of an issue. Why is that? Well, in this example, we used a vector of a string, but in actuality, most of the use cases are some sort of custom struct. They would probably just have a method on it. So you have a class that has another method that will actually just do both things for you under the lock. So this is quite useful. Scope guard, a generalization of the RAII interface. I believe this is actually a proposal for the standard. We use this to great effect in our code base. I believe the proposal is called scope exit, and Boost, I think, also has some macro versions of it. Essentially, it's the same thing, but generalizing it to anything you want. When the scope exits, you can do something at all. So this is almost an exact case I've written before. Friends, you want to push something back in a vector and then pop it after you do some other work. If you don't use this and you just put that pop back at the very end of the function, it'll work fine most of the time. The times it will really bite you is when there's an exception. And that's actually, I've written that exact bug before, like, oops, I forgot to take care of this exceptional case. And so you don't want to wrap every single exception with a try catch, so use a RAII scope guard or scope exit instead. So if you guys did watch the really awesome string talk yesterday, he talked about, we have these small value optimizations, we have copy on write optimizations, all sorts of things, like little tricks to try and make things go faster. It turns out if you have a non-owning string, if you know the lifetime of the string is going to exceed when you want to use it, using something like a string piece, just a non-owning string type. I think the standard proposal is string view. It's much faster. It's faster than all those. You just have the pointer to the start and to the end, and that's all you really need. It'll still do the range checking. It can be a view into some other data. It can be whatever you really want it to be. We also have generalizations of this based on any container type and not just string. Generally, people don't write this the first time around. In their code, they go through and say, I want to just use std-string or our version of FBString, and then write that throughout their code. And then they'll notice later, like in a perf profile, they'll go through and say, hey, this string copying is actually hurting performance a little bit. Let's go through and write in these string pieces in all the right places. Exceptions. Facebook is very pragmatic about exceptions. There's a lot of different ways you can deal with exceptions. Exceptions are very useful. You can throw and catch them without having to muck up all your control flow with a bunch of return values in various places. They have a couple of different problems though. They definitely cause performance issues if you use them in cases that are not exceptional. They're also sometimes harder to debug than they should be. You don't actually know sometimes where the exception is thrown from. They could be rethrown and caught and change types. So we have a couple different tools in our library to try and help us deal with these in our code base. So generally what we'll do is we'll just go through and use exceptions in the normal way that everyone has been using them. We have a bunch of different exception types, a hierarchy of types. They all inherit from std exception. And let's say, for example, we have one that is like a thrift exception for our RPC framework. And then maybe we have one that is like a timeout exception that derives from that. So we had several different derivations of different exception types. Then we're going along in perf and we notice, hey, this is actually causing a performance issue in our code. We can see it actually, the throw and the catch, taking up a lot of CPU time. What do we do about that? We could, of course, just go through all of our code and say, we're going to convert the exception to a return type. We're going to make an enum of all the return values. Instead of timed out exception and whatever else, those would just be different numbers in the enum. That's not a very pragmatic way to deal with it. I mean, that's a lot of extra conversion over that you don't actually have to do. I mean, you could do that the first time too, but you have to handle all these different return cases. Instead, we have one tool to deal with it, one of many, exception wrapper. Essentially what this does, it's very similar to exception pointer, if you're familiar with that. So you have an exception pointer, and you can convert it to, then you get this pointer object you can carry around with you that is kind of like a return value and deal with it. If you had an exception pointer, you would then rethrow the exception. The catch here is that the rethrowing of the exception is really the expensive part. That's the part we want to try and avoid. Instead, we have this thing, exception wrapper, that just takes whatever exception type it is, grabs it by the dynamic type, just like exception pointer, as opposed to trying to pass around like std exception. And then instead of rethrowing it, we have a bunch of methods on it that will be kind of like catch statements based on the exception wrapper. So this is just a very pragmatic way of dealing with this. I'm hardly saying this is the best way to do it, but it allows you to change the minimum amount of code necessary to actually go through and convert your exceptions into return value types without actually having to return value types. So you don't have to manage two different return types. Just a small micro benchmark. It turns out throw and catch are extremely expensive versus just passing around return values, something like 53 times more expensive. One of our other exception tools is called Exception Tracer. Our platform is Linux. We run everything on Linux, 64-bit. On our platform, when you throw an exception, say you don't actually catch it anywhere in your program, so you finally get to main and exit main, it'll be like, okay, uncaught exception, program ends. Maybe it'll print out the what of the exception. It'll print out a little description of the string of what the exception did. What it won't tell you is where the exception was thrown from, which is very useful information to debug your program. So what Exception Tracer does, all it does is whenever it throws, it will grab the stack trace, attach it to the exception. It will also keep it in a little stack of various exceptions that you've thrown. If you then catch that exception, it'll record the stack trace. If you throw another exception, it'll record the stack trace. So you have this whole stack of stack traces that will help you debug your trace of exceptions as you go through your program. So it's a little bit of clever code. It makes the exceptions more expensive versus exception wrapper that is making them cheaper and easier to use. Exception tracer is actually making them more expensive, and just for debugging purposes to help you debug. So we have some other utility libraries. You guys are probably familiar with bits, the various bit operations we have in the standard library. We have std-vector bool, which it sounds like might be deprecated shortly. We have bit sets. I think there's a proposal for a various size bit set that can be dynamically set, dynamic bit set, I think it's called. So while a lot of the other talks at CppCon have been about, they have included bit sets and like you want to modify some bits, they've mostly been about trying to make your data smaller. And bits can definitely do that. If you want to store a bool, it can only take up one bit. Bits can also do a bunch of other things. Our Intel processors have a bunch of different hardware operations to deal with bit sets. They can do fancy things with bit sets. They can count how many bits are set. They can find the first set bit if you have in a 64-bit word. And a lot of other processors have these instructions as well. It would be really awesome if somehow in the standard we had access to all these different instructions. Since we don't, we have a couple tools to use these intrinsics for you. GCC gives you intrinsics. Almost all the compilers give you intrinsics to use these. So essentially we have a bit iterator that will iterate over the bits and like call the find first set instruction. So just as an example of why this might be useful, like why do you want to find the first set bit in a word? Like that doesn't make any sense. I just had used it last month. I was writing a timer wheel. So essentially, you have a bunch of bits that are set for when your timeout should fire next. you only want to set the closest timeout through the system timer. You don't want to have a whole bunch of different timeouts. You just want to call the expensive system call once. So to do that, you just find the closest timeout, and from there you can calculate what the next timeout is. So to find the next timeout, you have a bit set, and you say find for set. So it is essentially doing some sort of search. Instead of a binary search or a min heap, you're just doing find for set in the bit set. If your bit sets are fairly small, if your sets are small, 64 bits, it'll do it in one clock cycle. Of course, it will be linear on top of that. So if you have 256 bits, it's going to be 4 times that and take a little bit longer. But if you haven't used any sort of bit operations before, you should definitely look into them. For any sort of small set size, they're going to be much faster than, say, trying to do a binary search or some sort of heap. There's lots of other cool things you can do with bits. We don't have any sort of atomic bit set in the standard. There's atomic operations, but you'd have to do by hand all the different bit operations. Maybe you want to deal with endian and flip the bits around. We'll also have some operations for those. Highly used in the networking code, the primary place that we're converting between the different endian types. So when Folly was released 4 years ago, this is probably the class that made the most waves. We added some dynamic typing to C++. People were really excited about this. What did we use it for? Things like that. Since then, we have a bunch of different options that have come on the scene. There's various variant implementations, so like boost variant, or I think there's an std variant. There's optional types. I think there's an std any type. These are all roughly trying to solve the same problem. Dynamic goes a little bit further. We actually use it for a very specific use case, and our use case is parsing JSON mainly. Facebook is a web company. We interact with a lot of different dynamic languages. I mean, it's PHP is our primary code in our website. Also, JSON comes up all the time. So we're doing some JavaScript, and we want to pass the JSON data back and forth. Dynamic is very straightforward. It's just a wide type. In terms of dynamic types, it is larger than one of the other ones in dynamic languages. So it is a union of all the different types it could possibly be, as well as an enum of what the type actually is. And so you could think of this in some way as just some sort of variant with a predefined list of things that it could actually be. And what is that predefined list? It's exactly the things that you can have in JSON. So just as some examples, you can convert, you can set it to any type you want. You can convert between various different types. You, of course, have the object type, which is really just a map of different things you can put in it. The same way you can do in JSON. You notice up here we have the conversion utilities, as string, as int. These actually just use the conversion library that I was just explaining under the covers. So they're extremely fast, and they work extremely well. They still do range checking as well. And then, of course, the two most important methods when you're going to use dynamic are converting to and from JSON. So you want to parse some JSON, give it a string. It'll convert it into these dynamic types that you can deal with the same way you would in JavaScript. And it'll take anything that you've modified, and then it'll serialize it back out to a string. So in terms of our use case, once again, only JSON really. We don't use dynamic hardly anywhere else in our code base. We use variant quite a bit, but only for like several different types, not nearly as big as this dynamic typing system. All right, we're going to slow it down a little bit and dive into a little more depth on some of these next ones. I hope you guys are all familiar with ThreadLocals, ThreadLocal variables. I love ThreadLocal variables. They're one of my favorites. I probably use them too much. We're really spoiled for choice. When you're talking about ThreadLocals, we have so many different choices for the ways you can create them. pthread key create, one of the most portable ways. It also has the most flexibility with a bunch of different ways you can create and use these pthreads. Excuse me, ThreadLocals. GCC has an intrinsic __ thread. C++11 has some sort of ThreadLocal keyword. Boost has a thread-specific pointer. We have a couple ThreadLocal and ThreadLocal pointer. It's a bunch of different choices. Let's dive in and figure out how they all work. To make a fast ThreadLocal, it actually requires dealing with compile time, link time, and runtime. ThreadLocal is just like everything is everywhere. You kind of have to dive in and work on them all at the same time to make them fast. So if we're going to make a very simple ThreadLocal to try and explain how these work, first you'd want to know exactly where your thread data is at. So every thread has some data associated with it. For example, it has a name, it has an ID, it has a bunch of ThreadLocals, it has other things associated with it, like probably priorities. has a sleeping state or a running state. So you grab your thread ID. Say we can call the Linux system call, get TID. pthread has a similar call. So we grab our thread data somehow. We index into our ThreadLocal data using a pointer. And then with ThreadLocal data, we have a bunch of different ThreadLocals. How do we know which ThreadLocal? Well, really, that's the pthread key create here. What we're doing is you have to call pthread key create before you can actually go and use your ThreadLocal. So it will give you some index, essentially, into your ThreadLocal data. It'll say, hey, pthread key create, you're the first one, you're going to get 0. So go use index 0. Great. So we can go index into our, probably a vector, because pthread key create doesn't know how many ThreadLocals there's going to be. So it will index into the first one. So there's a bunch of tricks we can play here to make these faster. If we're compiling everything statically, if we know the whole world, we know every single ThreadLocal that we're ever going to use in our program, we can actually lay out this array at compile time. We know exactly where all the ThreadLocals are going to be. Instead of having to call pthread key create, it will just compile it in for you. So that's exactly what __thread is doing. It's saying, I know the whole world. I can actually just, at compile time, figure out a number that's going to go into your ThreadLocal right away. Great. So Facebook actually does compile the world statically, makes a giant binary, and ships it out to all our machines. This is hardly the only reason we do that. It makes your ThreadLocals fast. It allows some algorithms using ThreadLocals that you wouldn't have been able to use before. It's not the only reason, though. Also, it carries all your dependencies with it, so which is kind of nice. But what happens if you're going to dynamically link things? What happens if you're going to be even more of a jerk to the system and DL open things? Really, you have no idea how many ThreadLocals are going to be, so you're kind of back to square one. What actually happens is a function gets called every time you access that ThreadLocal, called get TLS data, I think. So if you see something __TLS in your perf profiles or your profiles at all, that is what's happening, is that you have dynamically opened some library and it doesn't know how many ThreadLocals there are, so it has to ask at runtime where the ThreadLocal data is. So that kind of sucks. We could go even farther. If we actually want to get rid of this trying to figure out what our thread ID is, if you can arrange for the operating system to give you a little support and say, hey, I know exactly what your thread ID is. Every time we're going to preempt you, we're going to stick your thread ID in a specific place so you can figure it out. That would be a little bit more helpful. We wouldn't have to make a system call. On x86, we actually can go one step farther than that. We actually have hardware support for ThreadLocals. Way back before we had virtual memory, we had something called segmentation registers. We used to use segmentation registers to index into specific locations in memory instead of having a virtual memory system. We don't actually use these anymore. They're laying around empty and free, so we repurposed them for using ThreadLocals. So what Linux actually does is it will stick your pointer to your ThreadLocal data in the segmentation register. And then when the assembly code is generated, it will just prefix the segmentation register, fs colon, and then whatever variable you're trying to access in your ThreadLocal array. At the end of the day, what this means is you get extremely fast access to your ThreadLocals if you are statically linking the world and you're on x86. Probably other operating systems, but I don't use them, so I don't know. So it is actually the same speed to access a ThreadLocal using this scheme as it is to access a regular variable. Exactly the same speed. Cool, let's go back to our little chart here. What does that actually mean for our chart? pthread key create is the first one we investigated. If you're doing everything at runtime, pthread key create is the way to go. It actually has some extra hooks in there to help you out. For example, when the thread is destructed, you actually get a notification, and you could actually do some extra work if you want to destroy your pthread key. __thread works great for plain old data types. Anything that doesn't have constructors and destructors, it will work excellent. thread_local from C++11. If you have constructors and destructors, that's the way to go. That's probably just a general recommendation. Use the standard. Why not? It works great. It actually has a little bit tighter constraints in terms of when you can access it. So if you need to access your ThreadLocal data before main or after main, you may actually end up having to fall back to some of the intrinsics in the compilers. So we have these last three, thread-specific pointer and ThreadLocal pointer. What do those do? Well, so far we haven't talked about member variables, classes. C++ has classes, surprise. We have member variables, so we're going to make a member variable that is a thread local pointer. Currently, you cannot do that in the standard. There is no way. So that's why Boost has added thread-specific pointer. Folly has thread local pointer. For a motivating example for why you would want to do this, because I get that a lot, like this doesn't make any sense, why would you want to add one of those? We're just going to invent some class here that is a counter. Essentially, we're going to keep statistics for something. Let's say we want, every time a function is called, to keep a counter of how many times this function was called, and then we'll save it later. We'll print it out to a log message every minute or something. So if we just made this a global variable with a mutex, or even an atomic that we're going to atomically increment, that's going to be a lot of contention on a single place if it's called often. We ran into this case in our stats code all the time. It comes up very frequently, even on other cases that are less well contended. So what do? We make it a thread local pointer instead, or thread local instead. So with a thread local int, we then just increment a thread local. So accessing a local variable, a thread local even is the same speed as the local variable. Increment it once, great. Then we want to get the whole value of the whole thread local statistics counter. We use this access all threads method. And that's really the trick. That's pretty much the whole point of why we have a version of thread local in our library that no one else has really implemented. So you walk around all the different thread local threads, add up the value, and then you have gotten the global value for whatever it would have been if it was actually a global. So Boost thread specific pointer, it can be used as a member variable. It does not have the access all threads method. Folly thread local pointer do have the access all thread method. So there's a bunch of other use cases for this, and we're going to jump into some of them shortly. Singletons. I hope you guys are familiar with singletons. They're pretty easy, right? You have something, you just like stick it on the stack, like, okay, here's a static, we're going to make it a global. It works pretty well. It has a couple issues. If the singleton references other singletons, we could run into problems. There's a thing called the static initialization order fiasco. This is going to blow up all over. If you have two singletons that are referencing each other from different files, you don't actually know which one's constructor is going to run first. The linker it gets to choose which one is going to run. So we can fix that. We can make a new version of Singleton. We'll just make a method. It will go and make a new thing and return a new thing. So if you want to use a Singleton, great. We don't have any constructor order issues now. If new thing calls some other singleton in a different file, it'll work just fine because they'll all run at runtime and it will be well defined. There's also no destructors on this one. We're just leaking the memory everywhere, which can be an issue. That's great. We can solve that. There's this thing called the meyerSingleton. Hopefully you guys have all heard of the meyerSingleton. You just have a static item in your method and you return a reference to it. And this works great. It works great in the context of the C++ standard. If all you're going to do are things in the standard, you could just do this all day and it will work just well for you. My only gripe with this, it's just a tiny little gripe, is that it seems a little bit magic. You don't actually know what's going to happen here. This is what actually happens there. Several pages of assembly code, taking locks that you probably didn't expect. It calls and registers an add-exit handler so it can run the destructor. But it all works just fine. When it doesn't work, in the case that we have run into in actually using this in our very large production code base, is that it doesn't work in the case of using some of the POSIX interfaces like fork. So what does fork do? Well, it goes and duplicates your program and starts a new copy of it and continues running. Fork doesn't play very well with multi-threads. It doesn't play very well with open file descriptors. You have to worry about all these little subtle things that can happen when your program forks. If we were just talking about our code base in our C++ world, we could probably get around this and work around fork. We'll only call fork in like very specific small instances. Unfortunately, we don't control where all our code runs. Let's say we write ourselves a little library. We want to go and write some singleton, like a logger. We'll make it an asynchronous logger, so it can like open up a thread in the background, it'll open up a file, go and start writing to the file. Let's say now that we want to import our library that happens to use a singleton that is a logger and put it and use it from, say, a different context, like Python. We want to go and make this a Python extension. The problem with that is Python calls fork all the time. Python has a global interpreter lock, and of course, then you want to go and use multi-threading instead of threads, so you want to fork and make multiple copies of your Python process. You run into all sorts of trouble. This also comes up in other contexts and other languages, but the primary motivation is using your code as a library when you don't really control how it's going to be used. So instead of the meyerSingleton, we actually have something that is just a class. It's called Singleton. It takes a template parameter of what the actual singleton object is going to be. You can then call get on it, just giving it the type, because of course it's a singleton, so there can only be one of the type. You could also just grab it from the object itself if you wanted. And then the little bit of like automagic stuff is that you can say, I want to shut down all my singletons, and then I want to restart them later. So you shut down all your singletons before you call fork, and you can start them back up later. Fork isn't the only use case. You can say, in my unit tests, I want a clean world. I can just go and shut down all my singletons and restart them. Different things like that. This is really getting quite close to something like dependency injection. We're managing all our dependencies in the world in some way. So you might have noticed here that when you call singleton get, it actually is returning a shared pointer. So the reasoning for that is that you actually want to make sure all your singletons are in a quiescent state when you go to shut them down before you call fork or whatever you're going to do. So in the case of the logger, you want to make sure no one is actually using the logger when you try and go and quiesce the logger. So the way we do that is just use a shared pointer. When the shared pointer count goes down to 0, we know that no one is actually using it anymore. The problem with that is that this is a singleton. Having a bunch of people grab a shared pointer, increment the ref count, use it, decrement the ref count. The ref count is all on a single cache line. If this is happening from a bunch of different threads at the same time, as it might with like a logger singleton, is going to cause quite a few issues. So we want to make this shared pointer access a little bit faster. So we resorted to using RCU and writing a faster shared pointer. So our version has roughly the same interface as atomic shared pointer. I believe we called it read mostly shared pointer. What it does is essentially shards the reference count for the shared pointer into a bunch of different cache lines. It, of course, can do this in many different ways. One way you could do this is, say, using ThreadLocal. Now I just have a ThreadLocal reference count to whatever my singleton is. So using the ThreadLocal structure we saw before. Then when we want to go and shut down our singleton, at that point, we can say, hey, I'm going to go and round up all the different counts from all the different threads using access all threads. And then when they go to 0, then I can actually go and quiesce my singletons. Cool, we're going to talk about some of the synchronization primitives we have. The standard library gives us quite a few. We have std mutex, std condition variable, quite a few others. We have some high-level tools built on top of that. These are really the ones that we've found most useful for our large code base. So we have a multi-producer, multi-consumer queue. These have definitely been talked about elsewhere at CppCon. They're extremely useful. Ours is a lock-free version and a lock-free ring buffer. So we know our hardware. We know we have Linux. We use x86. Something that you may not know for x86 is that there's actually different strength of atomic operations. On x86 specifically, but not most other architectures, atomic increment is actually faster than the various CAS operations. So the npm-cq takes advantage of this fact by using an array, and you just basically grab a ticket and run around the array for each different insert or delete. So you could just go on the internet and say, hey, npm-cq, you don't have to use ours. Ours isn't like significantly different than most of the others. The one thing that we actually did find in production that was very useful is the ability to sleep. So you can either grab asynchronously the next object, say the queue is empty, and you want to go and say, I want to remove something from the queue. You could say that if it's empty, I'm just going to return right away. Or you might want to sleep and wait until something actually is inserted in the queue. This actually comes about because we actually have the way our programs are set up. So our hardware is fairly small Intel hardware. We have 32 cores, 64 cores, but our number of threads is much, much larger than that. Most of our programs run with somewhere between 500 and 1,000 threads. It seems like a phenomenal amount of threads. Most of them are sleeping and doing almost nothing. The problem comes is sometimes you run into these situations where there are more threads than cores trying to use this npmc queue or any queue or grabbing any lock really. And if you're using spin locks, if you're waiting in cast loops, you're going to be taking much longer and run into very bad situations because these cores are spinning, doing basically no work while they could be sleeping instead. So it's one of the very few changes we've added to npmc queue that is different from the average one you see. The standard is also a proposal for a shared mutex. This is basically just a reader-writer lock. So STD mutex is an exclusive lock. Anyone that grabs the lock has exclusive access to the data. Shared mutex is a reader-writer lock. There's a reader count and a writer count. There can be many different readers. They can all be accessing the data simultaneously. There can be one writer. And so you could have writer priority locks, you could have reader priority locks. That's really beside the point. What is necessary to know is that all these readers, at least in the current implementations that I've looked at, are all contending on a single cache line. There is the reader count, and they're all just incrementing and decrementing it, and it's one location. So there's a few scaling libraries. It's called a big reader lock. Concurrency Kit has one. There's a bunch of different papers on it. I think there was a cool talk on last year's CppCon about the big reader lock. Essentially what you're doing is you're taking this single cache line here that is happening on a single core and now splitting it across multiple cores. So again, we're sharding the cache line sharding the reader across multiple cores. You could of course do this with ThreadLocals as well. The current implementation just sets it up so there's one per core, but it doesn't make a huge difference either way. So one of the problems with the big reader lock is if we're taking this reader count, which is probably a very small size. We probably don't have that many readers. I mean, it probably fits in 2 bytes is plenty. Even 1 might be enough. The problem is we now need a whole cache line per core to store this. So we have, in our hardware, 64 bytes times 32, 64 cores, times the number of shared mutexes we have. So it really becomes an unmanageably large lock. And it was completely impractical to do it in that manner. And we definitely don't. We actually, this reader count here is not actually a reader count. It's actually just a linked list of the readers that are there. So this reader slot can be stored and can be shared among many different shared mutexes. So if you find someone who's already in your reader slot, you're just going to chain off him. So what this does is it means all those shared cache lines are actual global data. They're shared among all the different shared mutexes. That means they're not actually part of the shared mutex structure. It means our shared mutex implementation is about 4 bytes, which is very reasonable for a mutex. By comparison, a pthread mutex on Linux, std mutex is actually using the pthread mutex under the covers. It's about 40 bytes, so it's significantly bigger. And it's actually really surprising because you could go and write just an exclusive lock in Linux using footex system calls using about 2 bits. So using a whole series of bytes is extreme overkill. One other optimization we've stuck in here, because of the way we have actually sharded this, because these readers here are not actually a reader count, it's actually like a structure, like a linked list node that we're sticking in here. If your thread migrates from one core to another, it can't go and remove your little linked list node from the CPU it's on. It actually has to know which node it had locked on. So if between lock and unlock you're migrating CPUs, you actually have to go and slowly round up all of them. Instead of trying to search for your actual node, you could return a token from the lock method. So the lock method could say, hey, you are actually locked on CPU 1. If you're migrated somewhere else, you can just go and unhook from CPU 1. So it's another little optimization we've put in there. So another synchronization primitive we built on top of the standard library is called LeFosem. You guys are probably familiar with condition variables. So if you have several different threads that are waiting on a condition variable. If you have another thread that says wake 1, it wakes up one of those threads. Currently, it is undefined which of those threads are going to wake up. It's probably going to wake up the one that has been sleeping the longest. This is often not the ideal thing to do. You often want to wake them up in the last in, first out order. And let me give an example of what that means. So let's say we want to go and write an executor. This is just going to be a very simple thread pool. We're going to spin up a bunch of different threads that are going to do work. So if you have two threads, threads A and B, sitting here waiting to do some work. Thread C comes along and has finished its work. It's now waiting in the queue for something to do. Someone says, go do work W, go figure out something to do. The last thread that has entered the queue, in this example, thread C, has finished its work, and it was the first one, or the last one into the queue. It's going to grab work W and is going to be the first one out of the queue. So what this really does is it means if you write your implementation correctly, that C doesn't have to go through the scheduler. It may just be able to grab the work right away and go on and do some work. Its cache is still going to be hot. It was just doing work. Whatever it was doing is still in cache. Maybe it had some ThreadLocals in cache. If you were to wake up A or B instead, it would have to grab different ThreadLocals from the cache. So the cache is going to be extremely hot if you're using a last in, first out order. Just dropping this into our base thread pool implementation in a couple other places in our code, it ended up with about like a 1% latency reduction in a bunch of our different services. So I definitely recommend you try out something like this in your code. It was actually a bit tricky to implement. To implement it, you actually need to choose somehow which thread you're going to wake up. Mutex on Linux, fast user space mutexes, has a very large API, one of which is that you can choose using a bit set which thread you want to go and wake up. So that's the way ours is implemented. You can, of course, implement it in many other different ways. You could have each thread waiting on specific different condition variables and write it all in very portable C++11 code if you wanted. It'd end up being much larger and using more memory, though. So I have a little bit of time. We'll talk about a couple more things. Futures and executors. This has been covered pretty extensively at CppCon. So I'm really just going to share our experiences using executors and futures. We've written our own future. We had started when we were still on C++11. The standard future in C++11 is not very full-featured. It, of course, doesn't have the then method, which is the most important method for all of the futures. Then is really just like asynchronously chaining some work together. So your future, instead of waiting for it to finish for something to happen, you're just going to say, after you've done that work, go do some other work. And that works great. That's actually coming in 17, I believe. But there's a bunch of other very useful methods within when all, window, reduce. So if you want like a sliding window of different chaining items on your future, when all these different futures are done, then you can go and do something else. But really the one that I haven't seen too much talk about is the via implementation. And what this means is that we have these executors. There's been a lot of talk about them too. They do some work, you know, in a thread pool or something else. Like how do you use them together with futures? Really, this is the entire power of futures in my eyes. Like if you just have futures and you want to chain things together, like you could use callbacks and it wouldn't be that much different. But executors really take it to the next level. So a big example of this, going back to our asynchronous logger example, let's say that we want to make a futures interface to our asynchronous logger. You say, okay, go log something and let me know when you finish logging it. Well, the logger may happen in a different thread. So you say, okay, future, now go via over to the logger thread. Try and log. Maybe this logger could fail for some reason, so we have like a retrying method that will keep retrying this future. Catch some errors, maybe with on error. And then finally, we're going to via back to our current thread and keep running. So via is an extremely powerful tool. It's just a way to interact futures and executors together and make them jump between different threads. All right, so this is the last one I'm going to talk about. We have something called indexed mempool. This is a tool for writing lock-free data structures. It is a memory allocation thing. So there's a cool talk on Friday you guys should all go watch, talking about a safe memory reclamation. They're going to talk about hazard pointers. They're going to talk about RCU. There's all sorts of different ways to reclaim memory. Our choice has really been to do none of them. We don't reclaim memory at all. We just pre-allocate it all at the beginning of the program. And so the only other thing you have to worry about, instead of safe memory reclamation, is you have to worry about ABA. I probably don't have time in this talk to discuss ABA, but I hope if you're interested in lock-free programming and watched one of the other talks this week, that you've heard somewhat about the ABA problem. One of the ways that you could solve it is just to tag your pointers. So ABA means that you have a pointer, it changes somewhere, and then it changes back to the original pointer. And using a compare and swap atomic instruction, you don't actually know that it has changed in between, that there may be some things in like the linked list that have changed otherwise. So to work around this problem, you tag your pointers. Every time you access this pointer with a CAS, you increment the tag. So now you have A1, B2, A3, and the A's are no longer the same anymore. So the question really becomes, how big does this tag have to be? On x86, current hardware only has 40 bits of virtual address space. This might not always be the case, but it is today. So we have, say, 16 extra bits free that we can go and play with. If your data is aligned, maybe you have some extra bits at the bottom. 8 by the line, maybe you have 3 extra bits. Maybe it's 16 by the line, you have 4. It turns out that is not enough. Not enough bits to solve the ABA problem. In fact, I went and gave it a try. I took one of our lock-free data structures. I solved the ABA problem just using a tag. I gave it 16 bits to play with. It went and crashed every 6 hours or so. So instead, what you can do is just write a very simple memory allocator that manages your memory. It doesn't even have to be a real memory allocator. It's just giving you out fixed node objects. And all it's going to do is ensure that all these things line up in such a way that they only use 32 bits of address space. So you could just go mmap a large section of memory and hand out different pieces of this memory as long as the memory is less than 4 gigabytes of space or so. With the other 32 bits, you can go and use them to add your tag. This code is actually extremely short, extremely easy way to solve any sort of ABAs you're having in lock-free programming. It's all standards compliant. There's hardly anything that you have to worry about. It does use mmap, but you could also just use malloc as well and grab a piece from whatever allocator you're using. So go and compare and contrast this code to what you might learn on Friday's talk about safe memory reclamation. So that was my short overview of Folly. There's probably about 50 other utilities in there of varying levels of usefulness. I'd suggest you guys all go check it out. It's on GitHub.